Hi Shane, welcome. Okay, we are recording now. So let's start another section from the quantum key. Today we'll start with some discussion about the many words interpretation. That we call today many word interpretation. Uh, Sorry, I didn't put too much math today. I will give just a brief general idea, and because like the other course is taking, I'm finishing the quantum hardware course, and in this end is taking some times to make the calculations. So in the next quantum T, I'll bring some math. Today is just the general broadly ideas and a little bit of history, just a little bit, to start the discussion. So let me share these slides. Okay, so here another quantum T section. So we start today many words interpretation. Let's see a little bit, some few slides about the initial Everett's idea. So I decided to start like showing a little bit of history, just in the beginning, especially about Everett, because it's like the type of thing that we heard about multiverses and many words interpretation. But I think the name of Everett is not so popular. So I decided like to put a little bit of his story when he started like these ideas. So in 1953, who Everett III started his grad as a graduate student at Princeton University, supervised by John Archibald Wheeler, that was by that time already famous physicist. He works. I think he started work with nuclear physics, and then he decided like works as well with general relativity and cosmology. He has a famous book. He and other three authors about the book is called Gravitation. It's a very big book about general relativity. Yeah, it's Wheeler, Misner, and Kip Thorne. That was his student by that time. Thorne that was laureate with the Nobel Prize by the when discovered when the first gravitational waves was detected, 2015, I think. Kip Thorne was one of the Wheeler students as well that worked with general relativity and gravitational waves. So Maddow and Everett started like his graduate as a graduate student, and he finished not physics but engineer, chemical engineer in the university, and then he applied for as a grad student in the physics department in Princeton. So in 57, he presented his thesis with this title here on the foundations of quantum mechanics. And the same year, he published a paper that's called Relative State Formulation of Quantum Mechanics. And in this paper, he proposed this new formulation of quantum theory. And he said, because of the interests of Wheeler as well, it's better, it's proper for application on general relativity, because by the time we already know that the formalism of the usual quantum mechanics, when we try to apply to gravity, like using general relativity, it fails. It works for the electrodynamics, but it fails general relativity when you try to quantize the gravity. In 59, so he finished his PhD in 57. So in 59, he traveled to Copenhagen to show his results to Niels Bohr group. However, these results and his results, the Everett results, were not well accepted, and most of his ideas was like rejected. And by the time here, he was already like working at American Pentagon and has stopped his academic career. So about this, what I could read is like the people from Copenhagen, from Niels Bohr group, like say like this guy know nothing about quantum mechanics, and these ideas are like there's no sense, and he was really like a deception for Everett when this he heard about the people from Niels Bohr group ideas. I think one of us Rosenfeld that well, didn't accept his ideas. So so this was like stopped in 59. Everett was working the Pentagon, stopped his academic career, but in 1967, Bryce DeWitt used Everett's ideas to give rise to his program of quantization of gravity, because it seems that was more proper to use like these ideas to when you try like to use in gravity as well. I mean, the space-time as a whole. For instance, when you try to apply to cosmology. So we will discuss this today a little bit, just a little bit in the end. So in 71, probably it was the first time that the term many worlds appears in a publication. So by this time here, Everett didn't, in his thesis, he avoided to use the term many worlds or multiverses of all these things. Instead, he used like the expression relative state that he was using. So in about 1771, that the term many worlds was appears in a publication by DeWitt as well. So in 77, Everett participated in a conference about his ideas in a new generation of physicists that include David Deutsch, helping its developments, these developments of the Everett's ideas. And with David Deutsch came the ideas of multiverse, but we will not discuss a little bit too much today about David Deutsch because it's also related with quantum computing. So maybe in the future we will have more. At least I didn't prepare anything about this today. So in 1982, like Everett was the years of Everett's death. So this interpretation, this is just a close summary of Everett's history related with his ideas and many words interpretation. So this interpretation of quantum mechanics has become one of the favorite views for cosmologists and particle physicists, since they are most interested in the quantization of the gravitational field. And one of the advantages is that the theory where the Lorentz group is satisfied, as in the Broglie-Bohm theory, the collapse postulate is not necessary, and you will see that this is important when we try to apply this to cosmology, to the universe. And it is a quantum theory that is applicable in any physical system. Okay, so here a little bit about the theory. In the next, I'll bring a little. I'll bring some math today. I didn't prepare anything with math, so just to give just the idea. So it seems that Everett never used the term many worlds in his papers. Instead, he used the expression different states from the same physical system. The idea of many worlds turns out to be used by DeWitt in 1971. However, this was not consensual since the term many minds was also used. This for I forgot the name of the Indian reference for. I forget the name of the author. Broadly speaking, but this is related to something with consciousness. I think you start talking about consciousness in these ideas of many minds. I'll not talk about this today, but maybe in the future we can discuss a little bit. And broadly speaking, Everett was interested in obtaining a formulation to quantum mechanics that could apply to any physical system, including systems that are not subject to external observation. And as we could like see, this is important when you apply to the universe, because the question is, who is the external observation? Who is this external observer when you try to apply like the Copenhagen interpretation to the universe? This brings problems. So in the fundamental principles of this new view, there wasn't any reference to the external classical world of the physical system. So classical mechanics was just like a subproduct of the quantum theory. And in this context, it follows these three hypotheses here. So in any physical system subject to external observation can be considered as part of a large isolated system. Two, there always exists a complex wave function able to provide a complete mathematical description of an isolated physical system, including the universe itself. And third, the evolution of this wave function is linear and unitary in any situation, and in general is described by the Schrödinger equation. So this theory is deterministic, where every physical system is completely described by a mathematical entity that's the psi, the wave function, whose value is well determined by any time when you use like the Schrödinger equation. So let's see, this is a little bit of basic of the theory. We'll develop this in other section more when I bring like some extra math. So let's see only some applications here. One, when you have like the superposition, when you consider a system superposition state like this, to interpret the measurement output of this state, Everett considered the observed split between two different states. Thus, one of these states corresponds to 0 and the other to 1. Even though Everett was not clear about the nature of this split, what the nature of the cause of this split. So sometimes this interpretation is called Everett's relative state interpretation, where one observer state corresponds to 0 and the other to 1, relative to the first. So the origin of the quantum probability is just a subjective probability imposed by the observer. Another application is in cosmology. So in the orthodox, the Copenhagen theory, a quantum system is considered to be isolated from the outside world. So we have the quantum system, and we have like the classical world that is not, in principle, is not interacting once you isolated the quantum system. So this system then interacts with the classical apparatus, that's the classical world, that give the output result. So we have like as isolated quantum system, we have the Schrödinger equation, we solve this equation, and we have the results. And then we have the results output, and then when we go to the lab, measure this output, is when we have this interaction between the classical and the quantum. So you have this separation of the quantum world and the classical world in the orthodox theory. So from quantum mechanical postulates, we suppose that the wave function collapse. This is the one of the von Neumann contribution, the postulate, the collapse postulate, right? And when we say isolated from the outside world, this sentence, it's supposed to, it is supposed, we are supposing the existence of some boundaries in space-time that separates the classical from the quantum world. So, however, if you wish to apply this program to the entire universe, like to do cosmology with this, this would be a trouble to define these boundaries of the quantum system. Yeah, because who is this? Who is out of this world when you have the universe? So it seems that at least at this point the Copenhagen Orthodox interpretation didn't work well. And then we don't have this problem here, since we have defined here that the physical system is the same. I mean, you have just one physical system, that we don't have this separation between the classical and quantum part. Everything is part of the quantum system, and the classical world is just a sub-product, as he said. And this is in the Everett thesis. So, okay, and the idea of many worlds came with DeWitt. But so far, Everett was like talking about states, right? Different states, relative states. He didn't use this expression many words in any place. So it was DeWitt who interpreted Everett ideas, obscure ideas, to the many words interpretation. So here's in this paper, this Physics Today from 1970. I think he still don't use the term many words. I think he used many words in a book in 71. But unfortunately, I don't have this book, just the reference I put in the end. But here, this is the abstract of this paper. Could the solution of the dilemma of indeterminism be a universe in which all possible outcomes of an experiment actually occur? Question mark. And this is in part of the paper. It says that I shall focus on one that pictures the universe as continually splitting into a multiplicity of mutually unobservable but equally real worlds, in each one of which a measurement does give a definite result. Although this proposal leads to a bizarre world view, it may be the most satisfying answer yet advanced. So this is 1970. Okay, and then when this getting these ideas, these some references. I still didn't put this. I'll put all these slides that we are discussing in the GitHub, but I still didn't have time. But in the end, when I finish the quantum hardware course, this part I will have more time, and I will organize like a folder in the GitHub from in the Zaiku account in the GitHub to put these slides. So, but here's some of the reference that I used today. So, yes, I think it was considering about many minds is Barrett, 1999. In this book here. Yeah, and this is the paper related with the, the paper related with the Everett thesis. And this is the book I didn't find this book, Foundations of Quantum Mechanics. That seems to be the first time that the term man words was used. Okay, so we finish here. And we are open for questions or comments. In the next, I'll bring some math, okay? Today, you just a general idea. So, you guys have some questions, comments? We are open. Yeah.
Yeah, I got one comment. In the in the description, you mentioned. Boy, we're getting a lot of reverb here. Is everyone else getting that?
Yeah, I think I have an echo.
Yeah, there's definitely an echo. But it talks about the fact that when you have when you measure something in an object that's in a state of superposition, it's the observer that splits, not the result. I thought that was kind of interesting.
Yeah, I think he used the expression, I don't know if I put
It was on page 5
observers.
or whatever, slide 5 or whatever.
Yeah, maybe it's to me it seems the is
Five.
To interpret the measurement output of this, Everett considered the observer splits between two different states. Yeah, the observer.
I'm not even sure what that means.
Yeah, I'm not really sure as well. Yeah,
well,
I thought like for Everett, because he used this relative state. So it's not clear to me, at least the things I was reading so far, whatever it really means by this. So I know that when David came and bring the ideas of many words, he was discussing with Everett about these ideas, and Everett agreed. I mean, it seems Everett liked the term he used, and it seems that Everett was. I'm not sure really if Everett has in mind like these ideas of many words, but what I could read too is that his advisor, the Wheeler, was like asking him to use more some appropriate words to avoid some like mysticism, something like that. So I'm here with the book, but I don't know exactly the term he used before. Use this term relative state. He used another, but it's not easy here. So this part here, I take this book that Diego suggests. In the end, in the last chapter, he talk about the. It's not a technical book, but he talk about the many words interpretation. But yeah, but to me, at least so far, it's not clear what Everett had in mind when he said this relative state. If he was thinking about different words or different observers, like because uh, when people, I didn't put here because to me it's not clear as well. When people say it's like many minds interpretation, that is related with the consciousness, and I prefer read a little bit more about this too, and that's why I didn't put here. But I don't know what Everett really means by this point when he says like relative states exactly. So I think Diego would say something.
Yeah, I mean, I haven't read Everett's thesis or paper in its original form, but if I were to guess, what he means here is that, you know, at least the way it's interpreted nowadays is that this splitting is just basically entanglement. So if you take that state in superposition, and let's say, so I don't know if you can show it up again, just that state of 1 over root 2, 0 plus 1. And now let's say that you can think of it as being a qubit in superposition, or let's say, you know, more physical, the spin of an electron in a superposition of being spin up and spin down. Right now, you can imagine bringing another electron close by that is spin up, and you make them interact so that they entangle. So now the entangled state could be a superposition of 0, 0 plus 1, 1. What that means is that now this electron, if whenever this electron is spin up, it means that the other one is spin down. So imagine the electron had consciousness, just you know, for a minute. So that electron knows that whenever he has spin up, the other one is spin up, and whenever he sees a spin down, the other electron is spin down. Right? He doesn't need to look at the other electron. Just by the fact that they're entangled, he knows that whenever he sees spin up, the other one spin up. Whenever he sees spin down, the other one spin down. Right? So that's the relative state they're talking about. That it's relative to whatever that electron is perceiving. Now, obviously, electrons don't have a consciousness, right?
Mhm.
But now take another electron, right, and entangle it, and another electron, and another, and an atom, and keep entangling particles to this until you form a conscious being, right? So now that conscious being, you could argue that could be in a superposition of having seen the spin of that electron pointing up, and a superposition, and another part of that superposition of having seen the electron spin down. So you can see that as you never perform a measurement, but everything that has entangled with this electron has split into two separate branches, right? And they're both equally real. So that's the relative state he's referring to. That, you know, if you have anytime you have a quantum object in superposition, if you make it interact with other quantum objects around it, they get entangled and they learn information about the state of it. And then everything is in a massive superposition. And then you could end up having conscious beings like ourselves being in superpositions of seeing something spin up or something spin down. But the measurement never really happened. The whole wave function still exists intact. It's just that one part of that superposition saw the spin up, another one saw the spin down. Now, obviously, this has a lot of, you know, philosophical implications, because what determines, you know, me seeing it spin down or spin down, spin up or spin down? So you could say, well, you know, it's 50-50, right, if it's an equal superposition. But then the once you change the probabilities of that superposition is where it starts getting complicated. Because what this means is that, let's say now you don't have an equal superposition of spin up and spin down. Let's say you have 99.9999999% of being spin up and the remaining percent of being spin down. Both events of entangling with each of the branches still happens, right? there's
Yeah.
still a version of me that sees spin down with very, very, very low probability. But then how is that any different than when it was 50-50 if that version is equally real, right? So then you could ask, well, what do the probability amplitudes even mean if everything is equally possible?
Mhm.
And the defenders of many worlds interpretations have some ways to explain how you perceive the probabilities, even though they're not really probabilities. It's just something that we as humans think look like probabilities, but it's a really complicated subject.
Mhm. Yeah, but I think this is more, I'm not sure, but I think it's more modern view, right? Everett. I'm
Well,
not sure if Everett was. I didn't read the thesis. I read just the paper, that paper that I mentioned. Not really
yeah,
sure. I have to read again. Mhm.
I
Not
I
really
think
sure.
this concepts of oh, sorry, I'm getting a lot of feedback.
Yeah, I think we have echo.
Yeah. Okay, I think it's gone. So the concept of entanglement and the relative state, I think he had a good understanding of that. At least back then, that was to some extent well understood. From what I've read, what he didn't really know too much about, which apparently comes out very naturally out of his theory, is the concept of decoherence. So this whole idea of being in superposition and having an equal likelihood of having the wave function spread out, the way you say, okay, you can no longer recombine these two branches and say, let's imagine you split into seeing spin up and spin down, and you find a way to recombine the two branches, and then you could say, oh yeah, I felt like I actually split into two separate branches and recombined. And while I was in that branch, this and that happened, and this other branch, this other thing happened. What prevents that from being an argument against the theory is the whole concept of decoherence. That once you have entangled so many objects or particles to the state, it's no longer feasible to recombine them. And I think that concept he did not have back then. So when it comes to the splitting, that's the part that maybe was not very clear when he developed the theory. But I think that the process of understanding entanglement and you being entangled with something and that's your relative state, I think that's exactly what he meant.
Mhm. Okay, so I will. I need to read again the paper. But you
Yeah,
have the thesis.
no, as I said, I have
Oh,
actually read his original work. This is just from this is all secondhand I've read in other places.
okay.
Yeah.
Yeah, I look forward to looking at the sources. It seems to me from Carlos' explanation today that there's a big difference between Everett and DeWitt, and that Everett's interpretation is really more about the knowledge of the observer. And that seems to me fairly straightforward. But if DeWitt is saying that the physical universe actually splits, then I got a problem starting with the conservation of everything.
Yeah, and yeah, just but I didn't put here, but we are also because Dewitt was like talking about the many worlds, and then after that, the David Deutsch, who is the one that talk about multiverse. And to me, it's not clear yet what's the difference, if has some difference about this both. That's why I didn't put here about the things I just mentioned, David Deutsch, but this is one of the things that I don't know if it's the same thing, just different words that are expressions that they are using. Or it's different, like universe, really, when David Deutsch say. And when they would say this is not these many words, is a new universe, or just, I don't know, the same, but to me, it's not clear yet. So I will intend to develop, but if you guys know the difference about, because here, what's this in the book you suggest, the Jim Baggot, when he talk about deal with first that basically the things, the summary I put here, and then he came with David Deutsch that applies for quantum computing. He tried to use this, and he used the expression like multiverse. But to me, it's not clear what's the difference, if it has some difference. Many words and multiverse. What the difference of this? But if you guys know something, okay, can. If not, I hope in the next we can like discuss these things.
In general, with all these interpretations, including Copenhagen, I am having a hard time understanding the meaning of complex probability, where it's got an amplitude and a phase. And that seems to be at the heart of all of these problems, whether it's, Copenhagen measurement, where you take you project that down to a real value between 0 and 1, and that's a probability. And in my mind, the central problem is understanding what the complex probability means. The paper that Diego recommended made that quite clear, that the difference in whether it's real or complex is in these probabilities and in information, and not so much in the physical system, at least as I understand it. So I guess I need to, none of these books that I've studied so far has really talked much about the Bohm rule, that part of the axioms. It's just given, so I need to learn more about that.
Yeah. So I think that is true, that what really differentiates all the different interpretations is, what do you do with this probability amplitudes, and does the wave function collapse, and then do they mean that this is a probability observing one thing or another, or in some interpretations of many worlds is more like is the weight that you assign to an event happening. And so, but you're right. I mean, what would it mean that is a complex number? What I was going to say is that there are a lot of there have been some efforts to derive the Bohm rule out of just the unitary representation of quantum mechanics. And some people say that there's always something that it's like an assumption that you have to make anyway, but I can also provide some references on some clever and interesting things in that area, especially from what's his name, Wolfgang Zurich. There's some interesting work from him on that. And it's related to what they will mean for the many worlds interpretation.
So while you're looking for Diego, so in the next talk, I'm thinking to give a little bit more technical. So maybe some of these questions can be answered. But we have a part here related with the Everett ideas and the many world ideas. So this book here is a little bit, unfortunately, it's only in Portuguese. We don't have in English, but it's more technical book. So it's where I put some math and I get some references to technical references. And in the next, I'm thinking to give understand a little bit the math part, and maybe some of these questions could be answered, I hope. But okay, but I mean, you have if you have like some references now, it could be helpful.
Yeah. Well, I have some references on deriving the Bohm rule from unitary quantum mechanics. But when it comes to the math of just Everettian quantum mechanics, I think that's actually fairly straightforward because it's just standard quantum mechanics without measurement. That's all it is. There's really no, that's part of the appeal of many worlds is that you don't need to change anything, just get rid of measurement.
Yeah, and that's why they use like as advantage, because it's simple, at least in principle. It's simple. Then we don't need to bring extra things like in Broglie, right? This sense would be like much simple theory.
Yeah.
You use just the Schrödinger equation. That's it.
Yeah, I think where the real issue with many worlds is trying to make sense out of probabilities, or not probable. Well, yeah. Why is it that when I perform a measurement on a system over and over again, I see, probabilities that derive from the Bohm rule? If, according to the theory, every branch of the wave function happens, why is it that what I see when I perform measurements is related to the probability amplitudes? That's the part that, and I think that the issue is that it's more on the philosophical side than the math side that makes it complicated.
Mm-hmm.
I do like the idea that, the deciding where your subsystem is kind of arbitrary, so that the whole system does include the lab and the observer. But of course, that's a much more complicated system that's harder to analyze mathematically than the simple one or two state isolated system.
Yeah.
I agree. And it has this advantage when we try to apply to the universe, because we don't have, like, if we want to do, what's the wave function of the universe.
Mm.
If you try to use like Copenhagen, this would be complicated.
And the universe as a whole runs into that observer problem in that we can only observe things within a light cone of where we are, not the whole universe.
Mm-hmm.
Again, the observer is a bit of a issue in relativity as well.
Mm-hmm.
The one bit of a hint of math I thought was interesting as you mentioned that the Everett interpretation is Lorentz invariant. Maybe we can get into that in a follow-up.
Yeah, this is one of the things. So in principle, I didn't check the details, but in principle it could be applied to special relativity.
Yeah, because that struck me as one of the biggest problems with de Broglie Bohm is Lorentz invariance.
Yeah, because I think it's only when you get the probabilities right in the Vogel-Bloom, you recover like the Poincaré group. So we have Minkowski metric and Lorentz invariance, but it's only when you get like the whole system, I think, in de Broglie-Bohm interpretation. And here it seems I still didn't see the details, but it seems we don't have these issues.
Yeah, I guess thinking back, it would be a question of is the pilot wave going at the speed of light or what?
Yeah.
But anyway, thank you. At least I have a better understanding of what many worlds, or call it Everett interpretation, is saying.
Yeah, but I intend like to bring more details in the next, like see a little bit the math. I think at least to me, with the math, I understand better the things. But Mohammed Reza has a comment here. So also, it may be the case that the Everettian interpretation enforces the ideas that there is no unique universe. Yeah, it will always be part of a collection. Yeah, I think this. For what I could read, for sure, that's what David Deutsch is referring this when he says multiverse. I still don't understand well the width, what he means by the many words. If it's the same thing or not.
Well, I don't know for sure if the distinction between many worlds and multiverse is what I'm going to say, but I know that there's different ways to even interpret Everettian quantum mechanics. So, for example, if you listen to Sean Carroll speak about it, the idea is that you have a system in superposition, and then there's entanglement. So let's say different particles start getting entangled with a system, and then the universe doesn't split until you have some amount of decoherence. So basically, when it's so the entanglement is so large that recombining it is not practically feasible. So then you said that the worlds have split, right, after decoherence. I think David Deutsch has a different view, and is that the splitting doesn't happen with decoherence, but the splitting happens every time you have a superposition, and you have splitting and recombining of universes all the time. So that's why I think he calls it a multiverse, because it's he talks a lot about, for example, in terms of quantum computing, that the power of quantum computing comes from many different branches of the multiverse helping each other carry part of the computation and then combining it into a result. So I don't know if that's what the difference between many worlds and multiverse is, but at least there's like these two main camps where splitting happens with decoherence, or splitting is happening constantly every time there's superposition and so on.
Well, I'm not sure that this is correct, but I think it enforces eventually upon you that the whole universe may be a part of something larger. Yeah, I'm aware of the distinction between the two interpretations, but I guess there's no escape from the idea that it finally will apply to the universe itself. But I'm open to further investigation, of course. I don't know enough about the idea.
Yeah, I think there's also this misconception that every time you have this splitting of the universes, you're creating more mass or creating more energy and so on.
Mm-hmm.
But that's really not the case, because everything is weighted by the probability amplitudes.
Yeah.
Or another way to think about it is, let's say you have an electron in an equal superposition of being spin up and spin down. So you could say, oh, that's a splitting, which is up and down. But if you think about it, an electron in a superposition of spin up and spin down has a deterministic state of being in, spin, let's say, positive in the x direction. So it's sometimes I try to think about this, multiverse or many worlds thing as not so much splitting into many different branches, but just changing the basis in which we are looking at things at, right? Because again, a superposition of spin up and spin down is two branches, but in another basis it's just one branch, right? So,
yeah. That's interesting. Yeah.
Our brains might perceive it as splitting, but maybe in a massive Hilbert space, it's just looking at things from a different point of view. But I don't know. I don't know if that's the right way of thinking about it.
But it seems to me that in Stern-Gerlach there is a split, that you get these two lines.
There's the problem with measurement, I guess.
Well,
again.
Yeah. Well, in that case, you see two lines because you have repeated the experiment over and over and over again, right? Is the basis in which you perform that measurement.
Again, measurement.
Okay, yeah, the entire experimental setup, the directions of everything, yeah.
Yeah. So if you think about it, yeah, the electron is in a superposition of spin up and spin down, and then when the measurement happens, you as a conscious being only sees a dot on the top part of the screen, but there's an equal part of you that saw it on the bottom part of the screen, but from a different angle, you still see everything in superposition. So it's a single branch. Just that our brains, operate in a way where you can only see things in that basis, because that's the one you use to perform that local measurement. But from a outside point of view, you could say, oh, but I see two of you in superposition from this basis, right?
So if you could do the experiment just once with exactly one electron, I don't know if that's physically possible.
Yeah.
What would happen? That one experiment would just randomly be either one dot up high and one dot down below is what you would see?
Yeah, so let's say you are in the lab right now and you have one electron and you run this experiment. There's a 50-50 chance that it will go up or down from your point of view.
Yeah.
Right. So you perform the experiment, you see it landed on the top part of the screen. According to Everettian quantum mechanics, what you saw is not really what happened. There's another version of you that saw that experiment where the same electron landed on the bottom part of the screen. But in reality, it's not that the two things happened separately, is that everything is still in a superposition. So if there was an external being watching you and this whole experiment, they would still see a superposition of a version of you with the electron having hit the screen of the electron hitting at the bottom of the screen, and another version of you at the top. Again, like Carlos said, this is so much easier if you write down the math just in terms of entanglement.
Diego, sounds like what you're kind of supporting, the original comment I made about what's interesting about this is that the observer splits, not necessarily the universe.
Yeah. Well,
when you take a measurement, you split yourself into two possibilities, up or down.
So I think that's the point I'm trying to make, that from our point of view, it would seem like things split. But maybe from if you look at a high dimensional Hilbert space of it, and you look at the right basis, things never split. It's just a different.
There's two observations.
It's a different way to look at the state.
Yeah, it's like there are two of us looking at an elephant. We both see different things.
Sure.
The observer. It's what the observer sees, what becomes relevant. And the different possibility means that observers are splitting, and the same observer sees different things.
Yeah, and I think that's what Everett meant by the relative state. There's a version of me that has a relative state where the electron landed on the bottom part of the screen, and there's another relative state where he sees it at the top part of the screen.
So
that's the relative part of it.
Yes, I think it's
more. It's all relative to the observation you make. Is all relative.
I think it's all relative to whichever conscious being is analyzing that problem at that point.
The person who's doing the measurement, the observer, is actually being observed or measured. And that person, the observer, is in superposition.
Yes.
According from the perspective of that third party.
From a larger Hilbert space standpoint, because you can think of the wall, the screen, also being all a quantum mechanical object, and then from a higher dimensional Hilbert space, that screen is also in a superposition.
Yeah, I think this is the when they say like the whole. Everything like this quantum, like the quantum system, is the whole process. You don't have this separation.
Yeah. Which I mean, yeah. Sorry, go ahead.
So, go ahead, Diego. Go ahead.
I don't know. I think it was George. Hold on.
So in that sense, taking a projection operator in a Hilbert space only affects the lower dimensional subspace. The higher dimensional situation is unchanged.
Yeah, so that's the whole thing about projector operators, that they are local, right? They're supposed to be only a way to trace out the rest of the system.
Yeah.
Right. Yeah, actually, that's not quite right. The tracing out is before the projection happens. The projection is just, it's what you would use to this is gonna get too philosophical now. And what you would use to take this higher dimensional Hilbert space and bring it down to your own reality.
Yeah, I'm
because
thinking,
you don't see the other part of it, right? So for you, it's like it doesn't exist. So you project it into your own reality.
well, that's the entire experimental setup gives you the basis of the substate that the projection is going into.
Yes, it gives you the subspace. So tracing out the rest of it will give you all the possibilities, and then the projector will give you only one of all those possibilities. And you will use the projector that matches your reality, right?
Yeah, so the entire experiment is just creating a basis. You know, pointing your stern go like
Well,
in a certain direction and so forth.
yeah. So creating the basis is what decoherence does for you, because what decoherence does is it gets rid of the coherent terms of the wave function, and it gives you a system with the probabilities of seeing all the different possible projections, and then you use the projector to get the result you need. Now, the thing about Everettian quantum mechanics is that there's no projectors, right? Well, I guess you have to use them if you want to, match a certain result of your experiment with or match an observation with the what you have for the global wave function. So the math stays the same, but the idea is that projectors are not real. They're not physical. It's just a mathematical tool. In standard quantum mechanics, projectors, which are measurements, or the what you would use to model a measurement, are allegedly real physical things that happen.
And of course, mathematically, the key thing is that the projector is not unitary.
Correct. So many worlds, the whole idea behind many worlds or Everettian quantum mechanics is that everything is unitary. So if you're using a projector, it's just something to remove part of the system so that you can mathematically extract something local that you would observe. But the physical part of it, the reality of it, is that everything still remains in a superposition. All the evolution is still unitary. So the projector is just a mathematical tool.
Yes.
In
So it's
Copenhagen
like,
interpretation, it's real. It's supposedly a physical process.
yeah, but so in Everettian, it's like you have a projection here and a projection right there, right? Would be like two different projections. So you measure something local here, but you have another local in another part. And the total is unitary
Correct.
because they are like the superposition. It exists, is always there. And just like in one branch, you don't have the superposition anymore, in the other you don't have anymore. But a more global thing, so you all the things are still in superposition.
That's right.
Yeah.
And I mean, to me, it's hard not to see this as something very appealing, right? I mean, if everything is made out of quantum particles, why wouldn't everything be unitary, right? So if these projectors are real physical things, what's causing them? I guess that's where, those other spontaneous collapse theories say that maybe it's gravity, maybe it's just randomness and so on, but it just seems so unphysical that it's hard not to find many worlds appealing, from at least from that standpoint, right?
Yes.
So essentially,
We
the
know-
most separation goes from quantum to classical physics, right? So
Yeah, there wouldn't be separation.
that's what
I don't know if the problem is here, but I can read Muhammad Sana.
Yeah, I cannot hear.
Yeah, Carlos, to address a question you had earlier
Yes.
about the difference between many worlds and multiverse. I think the distinction might be purely one of grammar. That multiverse is a noun. It means a universe that consists of it's an object that consists of an infinite amount of parallel universes. Many worlds, I think, is the adjective. The many worlds theory one of the things that drops out of the many worlds theory is a multiverse. So I think one is the object and one is the adjective. I've got a
I'm
paper
not
here that
quite
just
so
uses it.
sure though, because I think the problem, you might be right that that's how some people might see, but I think the problem is that not everybody uses it that way, because I've heard many interviews with David Deutsch where he says he doesn't purposely use the term many worlds. He uses multiverse. I can't remember exactly the reasoning, but he makes a distinction.
Okay. Yeah, and I guess the question is it possible to have a many worlds theory without a multiverse? Or, the way to use the multiverse theory to get.
Yeah, I think that's my question, I think, in the beginning. But I think Muhammad Reza was trying to say something, but you have some problem with your connection, Muhammad Reza, please.
Yeah, I just wanted to say that I put in the chat the reasoning that I think applies to this case, that eventually there is no escape from the concept of multiverse in the Everettian paradigm. I think, I'm not sure, but I have to investigate further. Yeah, and that was my reasoning. Yeah, that was it.
Yeah, and then just to the idea of multiverse, I think it starts with this these things, but we can, when we study cosmology, it could appear. I think the because when we start like universe in the beginning of the universe in cosmologies, we have like the inflationary universe, something that happens. Though we have like Big Bang, like because it doesn't have theory, or a time 10 to the minus 43 seconds.
So are you talking about
after the Big Bang?
Inflation of the universe?
Yeah, inflation theory from cosmology, right? In the beginning,
Yeah. So that's another separate part of the term multiverse. But
yeah,
I think,
but yeah, they could not be connected. That's
yeah, that was the reasoning. That was the ultimate application of the Everettian paradigm. Because if you want to truly believe in the structure, that I think there's no place for holding off the concept of multiverse eventually. Yeah.
So, but I didn't get. You think it's not related? The things I'm
I
not
guess,
sure they are, but just
so. At the face of it, they're not. Obviously, they are not. But if you stretch the idea to its full potential, I guess there is no escape, according to the thing that I just put in the chat. But I'm not sure, obviously.
Yeah. So, any other points, comments? We have the discussion was very fruitful today. King George.
Yeah, I think it kind of comes back to what we started with in the very first quantum T, the philosophical meaning of what is real. And that these different interpretations are making different statements as to what is real. One extreme would be the Copenhagen interpretation, and the other might be the Einstein interpretation, where, there is this real universe, but we're not seeing all of it. And then so far it seems like the Broglie, Bohm, and Everett are trying to make different statements about what is real. But that's just my impression, and that's, I think, is really more of a philosophical question than a physics question. I mean, again, like, what would a different prediction be of an Everettian interpretation? Could you make an experiment which would say, okay, now we've shown this could only happen in the Everett way?
Yeah, a few weeks ago, or maybe months ago now, I did share a paper from Sean Carroll where he was looking into a possible experiment that could differentiate many worlds from Copenhagen. And the idea is based off measuring energy conservation. So I know that it might seem that many worlds doesn't conserve energy, that it gives you the illusion that you're creating energy, but that's not the case, because everything gets weighted by the probability amplitudes. However, in Copenhagen interpretation, there's a violation of energy conservation, because when the wave function collapses, then the amount of energy changes. And what the paper says is that actually people that are proponents of modern interpretations of the Copenhagen view precisely know this. So he proposes an experiment in which you could measure if this energy is being lost or not. So that will be a practical implication of it. Another implication is that even though you can't transfer information or communicate faster than the speed of light using entanglement, when you write the formalism in terms of standard quantum mechanics using measurements, the math shows that there are non-local effects happening. And that is a big problem when you try to marry quantum mechanics with general relativity. So some people say that standard quantum mechanics is a no-go if you want to find a theory that combines the two.
And of course,
Okay, go ahead.
sometimes a thought experiment 50, 60 years later can actually be done. I mean, at the time, Einstein was just making a thought experiment to which Copenhagen had no answer. But now in our time, the EPR experiment has been done, and one of locality or realism has to go.
Yes.
Myself, I'm happy to ditch locality.
Yeah, well, there's some people saying that you actually don't have to give up.
There's a third option.
There's a way to interpret quantum mechanics as a fully local theory as well, without giving away the notion of reality.
Aside from hidden.
But again, this is related. You have to, if you want to subscribe to that, you have to also believe that the multiverse interpretation is real.
Mm-hmm. Mm-hmm.
But that's kind of nice, right? That you can come up with a theory that is fully local and real without having to compromise in what we believe are important things to make quantum mechanics work with general relativity.
But of course, there's the disaster of multiverse, quote unquote.
But that's the thing. I mean, okay, it's getting kind of late for me. I'm going to have to go in a few minutes. But this is very interesting. But that's the thing that I used to be a multiverse hater. I just couldn't come to terms with it. I thought it was such a silly idea to have all this universe and so on. But the more I learn about it, the more I start feeling that this might be the way to go if you really want to make progress in fundamental questions of physics. And you said that there's the disaster of the multiverse, but once you start really looking into it, it's really not disastrous. I mean, there's really nothing unphysical about it. There is a problem. I still struggle with the issue with probabilities, but that's partly my problem because I haven't been able to understand some of the arguments where they say, you can make sense of probabilities, but in general, if you think about it, it's really not that disastrous.
I think that is a legitimate problem, first. And secondly, when you talked about the energy conservation violation in the Copenhagen interpretation, it was in conjunction with the Heisenberg uncertainty principle, right? Because otherwise it wouldn't make sense.
Yeah, I have to look back into it.
Because there is a violation of energy.
Yeah, I have to look again into it.
Yeah.
But one of the things from that paper, I'll share it again, is that even GRW theories, which are spontaneous collapse theories, people are proposing are well aware that there's a problem with conservation of energy. I can't remember all the details, but I can look back into it.
Okay.
But in any case, this has been great, but it's already 1:30 here. I'm going. Thanks, Carlos, again for organizing.
Thanks you guys.
Thank you, everyone. Thank you.
Yeah, thank you, Mohammed and Diego as well. This has really been a multi-way conversation.
Thanks, George.
Bye for now. Thanks.
Talk to you later. Bye.
Okay, bye. So see you guys next
Bye,
Friday, the quantum hardware, and then
okay, yeah, Friday is coming up.
yes. Next Friday, quantum hardware, and in the other Thursday, not this week, the next, we'll have the continuation from multiverse.
Okay.
So, okay.
Thank you.
See you guys. I will stop the recording. Thank you, guys, from people from YouTube. We are back in there. Let's see the next quantum T. It's in the 30. I included 30. Okay. So see you. Bye.